So in this manner, you are going to transfer the charge carriers under one electrode to the other electrode. Hence, storage of each adjacent cell accommodates bits of information. So we assume that each uh, cell is going to accommodate one bit information. So as soon as the charge is moved out of the electrode, say from G3 to G4, then the input gate is again put in a state to receive further bit of information. So as you move the charges to G4 finally, G1, G2, G3 are free now, right? So they can receive subsequent information to be stored. And as you see, these things happen very, very quickly. In clocks, the clock period is very, very small. It all happens in microseconds time. With just a fraction of second, the transfer is made from G1 to G3 by giving appropriate voltage. So the CCD behaves like a dynamic shift register. Register knowledge, it is a memory device which stores one bit information, and it is a shift register because charges are continuously shifted from one well to another well. And you see here, charge is transferred in less than 1 millisecond. So it is happening in a fraction of second. This is possible only when the charges is not stored for a long time for the inversion layer to be formed. In case the charge would disappear and the corresponding information would be lost. So they say that if you don't do the charge transfer within 1 millisecond, the electrons will try to escape out of the depletion layer, and all the information what you want to get stored will be completely lost because of this. That's why they say the charge has to be transferred within 1 millisecond or even less than 1 millisecond. See the last line. If you are going to take a longer time for doing that, the charges would disappear because they will always try to cross the depletion region, and the information, whatever you are trying to store, will be completely lost. So CCDs can be used as a memory storage devices. So full well means you consider it as a binary 1, and empty well means you consider it as binary 0. So however, charge storage depends on the associated capacitor. The charge has to be refreshed periodically. Otherwise, it will be permanently, the storage will not be permanent. It has to be refreshed periodically. So you have a metal you have a two metal layer followed by SiO2 layer followed by a P or N type region, right? So it forms a capacitor. So whatever capacitor has the capacity to store charge, only that much amount of charge can be stored, and you have to periodically refresh that charge storage. And CCDs can transfer up to 20 megahertz. In solid state imaging, the light may be shown on CCD from top or bottom for a charge transfer. So usually CCDs operate with electrical DC voltage, but even nowadays CCDs operating with light are available. So you can transfer, if you show light from either top or bottom of the device, the transfer of charges will be happening instantly. So separately, you will be having a photo sensing element which will detect light. So when light is shown on the CCD, the light will be converted into voltage, and that voltage will be will be sufficient to produce a charge carrier movement. So when you are going to have a light falling on CCD, it will generate the equivalent voltage, and that voltage will generate equal and opposite charge in the depletion region, so which will be affecting the charge transfer from one potential well to another potential well. So you can, the continuous shifting of these charges, you can use clock pulses for doing that. So you also have a matrix version of CCD which is operated, which will have a considerable application in the imaging field and TV cameras. So CCDs are used everywhere. For display also, you are going to use CCDs, charge coupled devices. So mainly the CCD is used in memory devices, in computers, in cameras, where you need to capture something and store it immediately. So those places the CCD is going to find a very good application. CCD is also used in photosensor arrays such as color signal processing elements, variable signal delay lines, and signal correlators. So other applications of CCDs is given here. So in the delay line, the time delay can be electronically varied by varying the clock frequency FC. So if you are going to use an n-bit CCD, the delay time is n by FC. So for moving the charge from one potential well to another potential well, you take some finite amount of time, right? So there will be some delay. So time delay is given by n by fc. So time delay will be proportional to n, because how much number of bits are there, that much proportional time delay you will be having when you're going to shift from the first bit to the last bit. So CCDs offer longer delays compared to surface acoustic wave devices. So delay line can be used as a building block for analog signal processing applications like transversal filters, recursive filters, pulse compressors, and pulse expanders. So these are the several applications of CCDs you have. The packing density is very, very large. It's 100 times great. So within a single square area of the device, you can fabricate several CCDs for memory devices. So the kind of power consumed by CCD is very, very small, so which will ensure the operation of CCDs at high frequencies. Okay, so this is what we have about the charge coupled devices. So charge coupled devices are basically a form of CTD. CTD is a charge transfer device. So two types of charge transfer device we have, CCD and BBD. We have only CCD in our syllabus, charge coupled device. So we studied about CCD, the basic structure of CCD, how it is constructed, and by applying voltage, we have seen how charges are periodically transferred from one potential well to another potential well. So, for example, you have shown only G1, G2, G3. You will have several hundreds of electrodes and potential wells. So, information will be initially it will pass sequentially from G1 to G100. So you cannot directly put information into G100. You have to sequentially transfer from G1 to G100. So that is going to take a lot of time. That is what we have said that to be the delay time. So for n bit CCD, the delay time TD will be equal to n by Fc, where n is the number of bits I am going to use for my CCD. Two important advantage of CCD is the packing density is very, 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 very good. So it is 100 times good, which means that in a very in a single area of wafer, I can fabricate more number of CCD devices which can be used for transferring charge from one potential well to another potential well. And also these CCDs consume very, very little power, because with just 5, 10 and 15 volt, I am achieving the complete charge transfer from G1 to G100, right? So these devices consume very, very little power, and they can operate at very high frequencies. So that is the advantage of using charge coupled devices.